essay question number 2 for Unit 3. Here on this chart, this graph is a cardiac cycle graph. So there's a few different things that happen here. So first we'll go through the portions of the graph and what they represent. So this first space here is what we call isovolumic contraction. This next bigger gap is the ejection period. This next small one is the isovolumic relaxation. This section here that spans these two barriers is passive inflow. And then we have the atrial systole section of the graph. So this graph is separated in half here with it going these two sections here. This top section is the pressure charts, and this is the volume charts as to what's happening at the same time as pressure and volume change. And also this whole section here is known as systolic, and this is diastolic here. So when your heart first goes through contraction, this is all happening in the left ventricle of the heart and in the aorta. So this blue line represents the pressure of the left ventricle. This light blue line here. This dark blue line is representative of the atrial pressure, the left atrial pressure, and then this gray line is the pressure in the aorta. So first we have the mitral valve, which separates the atrium and ventricle on the left side, close. That close first gives us this lub sound. It's the first heart sound. As this valve closes, the atrial ventricular valve will open. That is also known as the aortic semilunar valve. So we have a little increase of atrial pressure as that occurs, but we start to build pressure in the ventricle as it starts to get into its ejection phase, which is here. So it starts to increase until that valve opens and there's enough pressure, and then as it's ejecting, the pressure shoots up and then relaxes again. And the aortic pressure follows that same curve. And then right at the end of ejection, right when we hit the isovolumic relaxation stage, this semilunar valve closes, and that gives us our second heart sound, which is the dub. During this, the aorta, the semilunar valve closes, and the blood that didn't quite make it through the aortic arch and into the body rebounds, and it creates what we call the dicrotic notch here. And that can sometimes give a third small heart sound, but we don't consider it part of the lub-dub primary heart sound. It's sometimes there and sometimes is not. But as that atrial or the semilunar valve closes, the mitral valve will open again. During all of this, we have the end the end systolic volume of blood here. And so as we eject blood out of the ventricle and into the aorta, obviously we lose blood. Volume decreases. And as that aortic valve closes and that mitral valve starts to open again, obviously nothing happens. And then we call this the passive inflow. So at first, there is no pressure change as shown here because blood is just leaking into like an empty balloon. If you were to pour liquid into a balloon at first, it doesn't stretch, it fills the space it occupies, and then it would begin to stretch. So this is that passive inflow period, and it still goes through here, and then it will increase in volume, and it also increases in pressure, and then we would meet back here on this line at the very end. And that goes through one cardiac cycle. It does this over and over. As soon as it reaches this point again where the pressure starts to increase, As soon as it hits enough pressure here to open that valve, the whole thing starts over and it just goes over and over and over on this chart. But that is the cardiac cycle. Along with the cardiac cycle, we have a pressure volume loop, and this is a representation on a graph of what is going on just in the heart as a whole during that entire process. So this kind of boxy looking part is the contraction and relaxation of the heart. So we can see we have volume versus pressure on our graph. And we can see here that the distance between these two lines is what I've labeled as SV, or stroke volume. So as we move our volume across and we're increasing in volume, our pressure stays consistent. And here we get that preload. Preload is the amount of blood that we have in the ventricles pre-contraction. It's all of the blood that has filled those ventricles. And there is where the mitral valve closes. We get that lub. Once we build enough volume, we have a stark increase in pressure. This pressure will help us to move the blood up into the aorta. That's what we call the afterload. The afterload is everything. It's the amount of pressure that is needed to move the blood. So once we hit this on the afterload, that blood will move. We get it to leave the ventricle. And once we've left that ventricle, we hit here on the dub. We hit the semilunar valve closing. And once that semilunar valve has slammed shut, we get that second heart sound. Notice as we've gone across this graph, we only change one thing at a time. As we change volume, pressure doesn't change. Once we've reached a certain volume, pressure changes. Once we reach a certain pressure, volume again changes. And then once we reach a certain volume again, pressure changes. So we change one thing at a time as the factor that influences the next thing. So we have this line here also known as the inotropy line. And this line is measured as a slope. We can tell the elasticity or contractility of the heart based on this line. The steeper the line, say it was more so here or even higher, we would know that it takes more force to contract the heart. The heart is less elastic. Whereas if it was here, the heart was more elastic, and it doesn't take as hard of a squeeze on the heart, of a contraction on the heart to move that blood. But that is the basics of a pressure versus volume loop. There are also a few equations that kind of correlate to this, one of which is that the cardiac output is equal to the heart rate times the stroke volume, and you can take stroke volume further to equal the end diastolic volume subtracted from the end systolic volume. So if you know any of these and one is missing, then you would be able to figure out a cardiac output, or you could figure out what the heart rate would be if it would increase or if it would decrease. But for example here, this 120 is the end diastolic volume, and this 50 is the end systolic volume. So we take 120 minus 50, and we get 70. And that would be our stroke volume times whatever our heart rate was, just for simple math. Say our heart rate is just times 2. And our cardiac output would be 140 liters per minute, I believe the units are. But the units don't matter. It'd be 140. And this is helpful to know as we increase or decrease our stroke volume. We can correctly change the other variables to figure out what is going on in somebody's heart, and that can be very useful.